All right, let's get started. So last time we left off at the type 2 turbines, right? So type 2 turbines, this is just type 1 with the added resistance. Right? So all the equations stays the same, right? Except wherever you see R2, you substitute R2 plus R add. Right? So this is give me a second. I think the screen share is not showing up. We can talk about the midterm. So the midterm is next Thursday, right? So next Thursday, and we'll cover up to type 2 turbines. Okay, so for next midterm, we'll cover up to type 2 turbines. And okay, so it seems to be working now. So let me try. Okay, good. So we'll up to type 2. So this week's homework. So it includes this week's homework. So it includes the new homework. Right, so include this week's homework. So to give you some time, if you want to look at the homework solution, we will do, so the homework 5 is due next Wednesday at 5:59 p.m. Okay, so we'll do a little bit earlier than normal, right? So we want to post a solution right after. If you have questions, give you a chance to look at the solutions. Then we'll go into the midterm the next day. So this is a little bit shorter time than usual for this homework. And I think so for homeworks, one thing we'll do is, well, at the end of the quarter, I think we'll drop your lowest graded homework. Okay, so we'll adopt that policy. We'll drop the lowest graded one to smooth out this impact a little bit. Okay, so if you miss one homework, or in the future you will miss one homework, or one homework does very badly, I think the easiest thing is just to drop the homework with the lowest score. For example, for this next one, instead of not grading it, we're posting the homework together with the solution. I think it's better to have it due a little bit earlier and then post the solution afterwards, right? And since we're going to drop the lowest graded homework, so there should not be a huge impact for this several hours of difference on the due time, right? So and the midterm, again, this will be posted Thursday morning. Okay, so we'll post midterm on Thursday morning, give you a chance at Wednesday night to look at the solution for this homework. Right, and so type 2, so basically we'll finish type 2 in this class. Then we'll start looking at power electronics, but the coverage is up to type 2 turbines. And type 2 is finish this story basically everywhere. We substitute R2 with R2 plus R add. So that's basically it for all the equations. Of course, this gives you one more control variable, right? That leads to the good thing about type 2, with sort of a wider operating range, allows to have a higher pull-out power, right? So it has a bunch of consequences associated with having this sort of controllable resistance. But for all the equations, you're basically adding this number R at for R2. Any questions about the midterm or the next for this week's homework? Okay, so again for next Thursday, right? I will hold an office hour at the normal lecture time. So in case you have some questions about the midterm, you can come and ask them. Okay. So do you plan to take a look in the morning? Right? Do at least go through the midterm in the morning in case you have questions so you can ask. So don't wait, again, try not to wait until very late during the day and ask for then ask for some questions, right? So that will be hard for me to respond in time. Right? So if you can, try to take a look at midterm in the morning. Other questions? Other issues? Okay, so if not, let's keep going then. Let's finish type 2 today. So if you look at the type, right? So one thing with that for this type 2 is you can change your maximum power, right? What you can do is you can change your pull-out power. You can operate a higher pull-out power with this added resistance. Another thing you can do is you can keep the power constant if for example, if the slip changes. Okay, so this is one example. As I think of a generator operating at 1230 RPM. And if the wind speed increases, then the generator speed also increases, right? So you spin a little bit faster. But let's say we want to keep the developed power constant. Okay, so let's say I want the power out of this generator to be constant, right? So what resistance do I need to add to the rotor side to keep this constant? And then we want to compute, how much loss is in the system, right? So we're adding resistance because we want to keep this developed power constant, and we want to compute how much of the power is actually being burned through this resistance. How much power is going through the added resistance we're adding to the rotor to keep the developed power constant. So this is one example of what you can do with added resistance, right? So it allows you to operate a higher power or operate at the same power with a higher speed. All right, so if we look at this problem, so what is a synchronous speed then? So if the rotor speed, if the speed is 1230 RPM or 1260 RPM, what's the synchronous speed? All right, so you may very well get a question like this in the midterm, right? So it's good, it's important, right, to recognize the synchronous speed is 1200 RPM. Okay, so you're expected to be able to tell what the synchronous speed of the generator is, right? Since there are only few synchronous speed you can operate at. Okay, so this is expected. You'll be able to tell what this is, right? The question does not need to tell you. Okay, so if we look at without added resistance, so we don't have added resistance, then my speed is minus 0.025. And then the developed power from the equation, I think I forgot to tell you what the voltage is. So let's say the voltage is 690 volts. I think I forgot. Okay, so the voltage is 690 volts in this case. So what do I want? Right, so the same parameter as the last question. Okay, so for simplicity, let's use the same parameter as the last question. As previous example, so we have R2 prime is 10 milliohms, X2 prime is 100 milliohms. Okay, so let's take the same parameter as before, and if you take those parameters, then to compute the developed power, we have the standard equation. PD is -3, 1 minus S over S. The A1 squared, R2 prime, 2 prime S prime. Okay, so plugging all these numbers, we get 1.148 megawatts. So the idea is to have enough adder resistance, or add, to keep the developed power the same at a higher speed. Okay, so the goal is to, how do I keep developed power at this 1.148 megawatt for operating at the higher speed? So our new speed, right, the slip was the new speed, then our slip is 1200 minus 1260, this minus 0.05 is our new slip. So if you look at the equation we have, then basically we want 1.148 megawatt equals developed power equals to the case where you have this new added. So wherever you see R2, replace it with R2 plus R add. Right. So if you plug in the numbers, for R2 and X2, we can solve for R add. We can solve for this where R add is, right? There's a single equation, single variable. So how will you solve this equation? Any ideas? Right, since this midterm is you're open to computers, so you'll get some question like this. Right? So similar type to this, asking to solve for a variable, and the equation is not linear since you have a square here. So how will you solve for this kind of equations? Any ideas? So you get this in the midterm, and the midterm has this question: how will you solve for our add prime? Right, so I think Chad says get 0 on one side, use computer find x-intercept, right? So that's a graphing solution, right? So you can either use a nonlinear equation solver if you're very familiar with those kind of solvers, or the easiest thing to do is probably plot the following, right? What you can do is you can plot R add versus PD, right? You can look at the right-hand side and plot this. So R add cannot be smaller than 0. So you start from 0 and you plot this curve. There's some curve that you have some curve that goes up like this, basically. And then you can cross a curve with 1.148 and just read this off. Okay, and you can read this off as R add prime. So the easiest solution is probably just graph it, and read off where the intercept is. You can use a nonlinear equation solver to solve this. You can, so you can do, this is quadratic, so you can rearrange it, use a quadratic equation formula to solve this. All this are possible, but I'm expected that you will have some way of solving this problem. It's expected that for this nonlinear equations with a single variable, you'll be able to solve it. So in this case, if you just graph this, or however you want to solve it, we get our add prime. This is 0.0218 ohms. All right, we get this solution. Then the next step is to figure out, right, how much power is dissipated in this resistor. To do that, I need to figure out the current, right? Because I want to use I square R loss to figure out the power dissipated. So this is minus VA1 R2 prime R add prime over S plus JX2 prime. This is 618.77 extra degrees amps. So the power loss in the added resistor is 3R at prime IA2 squared. This is 25.04 kilowatt. Any question for this problem? Yeah. Right. So again, thing to remember is you're expected to solve this, right? So the difference between, say, this course, this time, and previously, since the exams are all done in class, in person, so the questions are limited to, the types you can solve using a calculator. Right? Now we don't have these limitations anymore, right? So you will get, at least one question like this, where by the end of the day you get a nonlinear equation and you have to solve it. So if you have, questions about this, or you're not sure how to do this, please ask. Right? Otherwise, in the midterm, you'll see, and the final, right? When we get to the final, you'll see questions like this. All right. So the chat also, there's a suggestion saying guess and check. Guess and check is a little bit tricky to use, right? Because it's hard to guess what the correct value is, right? So before solving this question, it's hard to know whether our add is 0.02, right? It's hard to know what the magnitude of these values are. So it's better to have a systematic way of solving this type of equations. And our equations are not very complicated. At most, there's one unknown. Okay, so graphing it is probably the best way to go, right? The easiest way to solve it. Okay. Right, so this is so those two examples, right? So this example is how do you keep the speed constant? And the example we covered last time is finding out the maximum torque and the speed. These are sort of very common questions we have for type 2. Okay? So for type 1, there's not much can be asked about type 1 because it's a very simple circuit. Right? There's not much to say about that circuit. Whereas for type 2, there's more things we can ask. Right? Since we have a free variable, there's added resistance, so there's a lot of more questions around this. So you want to think about all the different type of questions that can be asked, right? So if you change this added resistance, what can you do? And you're likely to see this type of questions. Okay. So next, let's think about type 2, right? So type 2 is nice, right? Sort of, since it has a much larger operating range. Higher pull-out power. Right, so it's definitely, you can get more max power out of it. You can have much larger operating range. But the tricky thing is, right, we need to install this RF. Right? I need to install added resistance somehow. So any ideas is how do we do this? Right, so physically, how do you put this resistors there? Right, so circuit-wise, we just drew a resistor saying, okay, I'm going to add this resistor to the loader. How do you exactly do this physically? Like you're going to build a type 2 machine, and let's say I want to add, 1 ohm of added resistance. How do I do it? Anybody have some familiarity with machines, right? So the difficulty comes from, so the stator side. Remember type 1, we can add resistance to the stator side. That's relatively easy because the stator side is stationary. Right? It's not spinning around. So you have some wiring and you add resistance. Here, you have a rotor that's spinning around. Okay, so the tricky thing comes from the fact that you have this thing that spins around, and you want to add resistance to it. Okay, so the wiring can get tricky to install that. Right? So any ideas how you can do that? So if you look at one of the sort of the early generations, the way you do it is you have to basically there is a slip ring system. Okay, so basically you have a slip ring motor, and that gives you a way to excise, basically run wires out of it. Okay, so there's a way to run wires out of it. That's very difficult. It's sort of hard to do. It makes the machine expensive. It's hard to maintain. So the newer generation is the resistance the resistance is basically installed in the rotating mass itself. Okay, this is so when you make the rotor, you basically embed the resistance. You embed the resistor inside the motor. Okay, so instead of having wires coming out, having resistors outside, as you put the resistors inside the motor itself. Okay, you put this resistor inside the motor to not have extra wires. Okay. But then the question becomes, how do you change the duty cycle? Right. So remember, our add is a dynamic quantity. Right. I want to control what our add is. The way we control it is through the duty cycle of the switching. Is the duty cycle of the switches. So if our goal is not to run wires into the rotor, right? The goal is, okay, let's not run wires. It's a big spinning machine. But then how do I do switching? How do I communicate to the switch what the switching frequency should be? So this is a true engineering problem, right? This is true engineering problem. In theory, we're done, right? We drew the circuit diagram saying there's some switch that dynamically changes the resistance. But actual engineering is, how do I do this? How do I communicate to the switch? How do say, okay, change your duty cycle, let's say from 40% to 60%, without adding wires, right? So we build the resistance inside the rotating mass itself to not have wires running around. But then now for this communication, how do I tell the switch to change the duty cycle? Any ideas? How do I communicate to the switches? So there's a suggestion called some wireless controller in the rotor. That is way too expensive for our purposes. We're not going to put wireless controller in the rotor. That's not really, and you have issues with wireless signal. Okay, you're basically in a fire cage if you do that. So it's not a great idea to do wireless communication. Any other suggestions? So we cannot communicate wirelessly, or definitely not in the sense of 4G and 5G. How do you do it? Any engineers? Any people? This, right? So this is sort of the practical engineering skills that goes into this. Okay. So the way you do it is you do optical signals. Right? So you cannot run wireless, right? So wireless, basically high frequency wireless in, say, the Wi-Fi frequency is probably no good, very expensive. But what you do is you basically have an optical signaling. Okay, you have built-in optical sensor onto the switches, and on the stator side, you can basically flash lights. Right? You do an optical signal, and this tells you what the correct duty cycle is. Okay, so you don't need very expensive wireless controllers. You basically need a cheap light sensor, right? You need a cheap light sensor that can, and then you build in the machine a way to the optical signal. So this sort of made type 2 much easier to use. Okay, so when there was a lot of wires, so it's quite difficult to construct the machine. And then people figure out you can build the resistors directly into the rotor. That's not very difficult to do. And then to communicate without wires, the easiest to do just do opticals. Just do a you just use a cheap sensor, and you can do it. Okay, so this is sort of what the type 2 you see today. They have this kind of structure. Any question about this? Okay, so this has the benefit also of being essentially unhackable, right? So this is not something you can hack. You cannot hack this controller very easily, or you cannot hack the signal very easily. So this was a sort of good solution for type 2. Of course, the drawback, there's still no reactive power, or there's cannot generate reactive power, right? So this is right. So we still cannot deal with reactive power issues. There's just not because we're adding a resistor, right? We're not adding a or we're not adding inductor or capacitor. So you're still the current, right, multiplied by the voltage still cannot give you immeasurate power. So you don't have reactive power. And this is another drawback. This is inefficient. Right? If your variable is a resistor, again, if whatever you're doing is changing the resistance value of something, then the current has to go through that resistor. And this leads to losses. You may have higher maximum power, but you will also have higher losses. So the goal is to somehow, right? So the innovation is, type 1, just the simplest thing we can think of. Type 2 is how to make it more controllable by adding resistors. And type 3 will be, can I do what type 2 did without adding resistors? And there are some better ways to control the system, but not burning the sort of I²R loss curve, okay? Improving efficiency. So that's a goal for type 3. Any questions about type 2? About more along these lines? Okay, so let's do a few more calculations about what other things you can do with type 2. And the higher level, these are the things that you want to solve when you design this sort of generation systems. Okay, so so another thing that type 2 can do is basically provides a better inrush current protection. So if you remember back to type 1, what type 1 tend to do is if the starting speed is high, and then you connect to the grid, there's a big surge of current, right? There's a big surge of current going through the system, and that may trigger some protection equipment. Okay? So type 2 is basically you can have this sort of added resistance, and this added resistance will reduce the current. Okay, will reduce the current. That's what type 2 allows you to do. Right? So let's see how does that work, right? So if you look at this type 2, right? So if you look at the inrush current, basically we want to understand, right? When you start at a high speed, right? When you start at a slip of the connection time. So here S is large, right, and negative. Okay, so S is large number, S is sort of high slip, that's large negative number. Then what I want to understand is how much of this current do I have going through the system? Okay, so what is IA1? How much starting current, inrush current, goes through the system? And we want to say, can I reduce that? Okay, is it possible to reduce this inrush current? Okay. So let's look at some numbers to compute, the impact this added resistance at the inrush current. So this example, similar to before, is basically a type 2 wind turbine. I want to compute with this 30 milliohms and without 30 milliohms, what is the starting current? What is the inrush current? What is this inrush current we have throughout going through the machine? So here we are going to use XM. Okay, so if you see a question, if XM is given, then we should use XM. We should use XM. We should basically use this equivalent circuit. Okay. All right, so let's compute the currents. Let's compute the currents we have in our machine. So the slip again is minus 0.025. Then the starting current, IA2, S plus JX2 prime. We're going to plug in all the numbers. Again, I want to say again, remember this dividing by root 3. Okay, so every time somebody forget to divide by root 3, right? Don't be that person. Divide by root 3 for this perfect phase current. So this IA2 is 0.2 degrees amps. Right, we want to know what the current in this magnetizing branch is. So we want to know what this IM is. I can subtract IM out from IA2 to get what IA1 is. So the IM is just the voltage over the inductance. This is J79.687 amps. So the stator inrush current IA2 minus IM. This is 950 angle 9.73 degrees amps. Okay. So this is without the added resistance, right? So we can repeat the calculation with the added resistance and let's see what happens. So with our add, then our IA2, right? So just have this R add in the equation. This becomes 248.5 angle 3.58 degrees amps. So now, of course, the magnetizing current doesn't change. This IM does not change. So the stator inrush current is IA2 again minus IM. This is 265.64 angle 21 degrees amps. All right, so this is the news current. So if you compare the two currents, the one with the added resistance is a lot lower. Right? So when you have this resistance, again, you can reduce the current in the system. So you can gradually, right? You can sort of, if you have this added resistance, you can gradually change it while keeping the current relatively smooth. And so you don't see a huge current spike when you connect the machine to the grid, when you connect the generator to the grid. Any questions about this? Okay, so the last thing we'll see, that was for say for the type 2 turbine is again stability, right? So turbine stability means So for us, the fault we worry most about is, again, that something happened to the grid side. Okay, so the grid side goes away. Okay, that's the thing we worry the most about, right? So here is, I say this lightning bulb means, something happened to the grid, okay, that have a large drop in voltage. And I can change the mechanical power input into the machine relatively slowly. That's a relatively slow process. Right? I have to pitch big blades. There's a lot of inertia in all those things. Right? Whereas again, my added resistance is electronically controlled. It's controlled by electronic switches. That can be done, right? Orders of magnitude faster than controlling a mechanical system. Right. So as when the fault first happens, for the first tenth or 100 milliseconds, it's really you want the electronics to kick in. Right. So the pitch will happen, reducing mechanical power will happen, but it takes time. Right. So the power electronics, the switching should help out during that phase of the fault. Okay. Right. So again, we can. Right. So this example, this is very similar to type 1. Where the excess power is dissipated by the SDR, right, at the stator side. Here, we're going to dissipate the power at the rotor side. Okay, we're going to dissipate power at the rotor side. We're going to dissipate, right? So we're going to see that if there's a fault, right, and the grid voltage is reduced for 50 milliseconds, how much power do I have to dissipate through this process? Okay. All right, so let's see what happens here, right? So what this question says is, I have something that's operating at steady state, but then a fault happens and the grid voltage drops to 80% of the steady state value. Then I want to say if I add this resistance, right? Add this resistance, and how much energy goes into this resistance. So what we can do first is let's compute the normal situation, right? When there's no fault. Okay, so no fault. At steady state, there's no added resistance. We have the developed power is -3, 1 minus S. X2 squared. This is 2 megawatts. Okay, so we have 2 megawatts. Now let's say the fault happened. Okay, let's say the fault happened, and I see sort of how much power, right? I see how much power we're now delivering. So when the fault happens, right? So now we have a voltage depression. Okay, so my 690 volts goes to 80%, 0.8 times 690. Okay. Right, so my output power is, and now I have an added resistance. So my developed power is -3, 1 minus S over S, 0.8 VA1, whole thing squared, R2 prime plus R add prime. Squared. And you do all this calculation, what you end up getting is okay, so the output power is quite a bit smaller. It's quite a bit smaller compared to before. So the power that has to be the power that goes into the added resistance. Right, so the power that's lost on the added resistance. This is 2 megawatt minus 320.18 kilowatt. And we get 1.79 megawatts. So we're, dumping this much power, right? So from this power, we can know the current. If we want, we have this as square root of the power divided by the resistance. This is 4.32 kiloamps. So this is the current we have through the system. And then, of course, the energy we dump through this resistor is the power multiplied by how long this voltage depression lasts. So this is 83.95 kilojoules. So this is what happens when we have a fault, right? So we have a voltage depression, and then we have a lot of power instead of going to the grid, basically gets dissipated in the resistors themselves. Any questions about this?
What is the voltage depression?
80%. So voltage to 80% of steady state value. So a fall reduces the grid voltage to 80% of the steady state value. So during the fault, we have 690 going to 0.8 times 690.
Okay, I got it. Thank you.
Yeah. Any other questions? Okay, so so you look at this resistors, right? They are burning a lot of power. Okay, so these are big resistors. These are not the tiny ones you see in some, the labs you have done, right? These are huge resistors. They have low resistance, but they have these are large in physical size. They have to take through this much current and power going through them, right? So these are not small things we're talking about, right? But the benefit is I can shoot, I can run a lot of current through them, basically. For a short time, you can run a lot of current through it. And this will allow you to stay connected to the grid for this 50 milliseconds, right? You don't have to disconnect from the grid. You don't have to do emergency shutdown, all that. You can stay connected to the grid, operating a little bit inefficiently for the time where you see a voltage depression. All right, so this is it for type 2. So these are sort of example questions I can ask for type 2. So take a look at the homework. Right? It should be up now. Take a look at homework. Do you pay attention to it, right? So a big part of midterm will be, type 2 and type 1 and type 2 turbines. All right, so with that, let's now take our break. So we'll come back at the 1:26. We'll then look at the power electronics to set up type 3. Okay, we'll do a review through power electronics because we're going to go away from the resistors and into more advanced circuitry, but we need to just refresh our mind in power electronics. So let's come back at the 1:26.
Would you mind scrolling down about half a page?
Sure.
Right about there.
Yeah.
Thank you.
Okay, let's get started again. So we're going to look at the power electronics. So everything here you should have seen before. So this is a quick review and give you a place to find all the equations, basically. Okay, so the idea is we're going to quickly look through all different types of converters we have and to set up next week's class for type 3, right, which is heavily power electronics based. So you look at power electronics, the most basic component for us, right, is a switch. Okay, so the most basic component for us is this ideal switch. Right, so we have a switch that if it's closed, it acts like a wire. If it's open, it acts like an open circuit. Right, so it can be on and off, this ideal switch. There's no ideal switches in nature, but for us, we'll assume our switches are ideal. We'll talk a little bit about the impact of non-ideal switches a little bit, but for most part, we're going to assume that if we see let's say a bipolar resistor, sorry, a bipolar transistor, that's an ideal switch for us. So this is our switch. Then if you look at the switch, it's categorized by this on and off timing, right? So the switch is described by being on and off. So if you look at the power and the time, the power and time curve, and then if it's on, we're passing all the power we have. If it's off, we pass nothing, right? And it's on again, we pass all the power we have. So this is called T on, this time. This is T on. This time that's off, this is T off. One period, including both T on and T off, is called tau. So tau, this is a period. And then so if this is P, this is PS, the average power we produce is the fraction of time we're on multiplied by the sort of the peak power we have. Right, so this is our sort of very simple switch with this effect. So this T on over tau, this is a duty cycle, often expressed as a fraction. So this is often denoted by K, which is the duty cycle of the switch. Right, so if you look at the energy, right, so we can look at energy. Okay, so energy is basically the average energy we output is the average power times the length of time we're looking at. Again, this is the duty cycle times the peak power times the length of time we're looking at this circuit. We're looking at this circuit. So for us, we will mostly care about average power and energy. Okay. So for us, what we care about, if you look at the power curve, right, it's not the same power going through the circuit all the time. Depending whether the switch is on or off, the instantaneous power changes. Okay. But when we do analysis, most of the time we worry about the average quantity or the average power through the circuit is. Okay. We won't worry too much about what the instantaneous power is. Okay, so
are all the variables with the S average?
Yes, in this case, yes. Yes, so we have the average quantities. So the notation will change slightly depending on whether we're talking about DC to DC or DC to AC, but it will be clear for each of the circuits. Okay.
Got it. Thank you.
Yeah. So if you look at the size, right? So of the switches, right? So it's interesting to look at the size of this thing, right? So if you work with, let's say, SI circuit, you work with integrated circuit, then you cannot see a transistor. Right? So they're integrated. You don't, billions of them on a chip. So you don't see an individual transistor. That's not the case for power transistors. So power transistors, these are sort of examples of power electronics devices. And they're not very small. These are not very small. So if you ever look at, for example, the board in a phone, or if you look at the board in your laptop, a lot of the things you will see by eye is actually the power transistors or the power electronic devices. Okay, so this is showing an example of how big they are, right? And by transistor standard, these are huge components. Okay, these are discrete components, right? So we don't deal with integrated circuits for power electronics. Power electronics, you're still looking at discrete components. Whereas I, you're looking at integrated circuits, right? And so a lot of them is actually there's a difference when you're looking at discrete components versus integrated circuits. Okay, so when we say topology of a power electronic circuit, we're talking about discrete, switches, inductors, capacitor, where they go. Whereas if you take classes in the VLSI, stream, you look at integrated design. Right? So there's, it's good to keep in mind the size difference of these things. So these are, again, not small devices. Okay, they're not small because they have to conduct a lot of power, right? So they have to survive. For example, if you're using a bipolar transistor as a switch, the bipolar transistor has to stop a lot of current from going through it. Right? So they cannot be made too small. So you have all this. Devices is another example where these are the bulky devices. Okay, so we don't need to do fabrication. Right? Often in power electronics, we don't do fabrication. You don't have to ship it to a foundry. The foundry does it for you. You got to ship back. These you can buy these sort of discrete components and install them in a circuit. Okay, so there are two kinds of people in power electronics. There are people who make these individual devices better. There are people who does topology, who sort of puts things together. Okay, so for this class, for sure, we'll only look at topology. We won't worry about how you make a device better. But if you're interested, there are other classes that really talks about, how do you make a device that can operate, let's say, under 1,000,000 volts? Right? How do you make a switch that can actually tolerate 1,000,000 volts? Right? So those are not easy things to construct, right? But so keep in mind that, again, these are sort of bulky devices, right? So you can buy them really off the shelf and put things together to make a circuit. Right, so there's another example. If you open up any board nowadays, right? So if you ever get a chance, open up any of the, open up a phone, for example. What you see, all the things you can see is probably the power conversion circuit. Okay, most of the things you see is the power conversion circuit. And if you look at, for example, an Apple phone, okay, so if you open the Apple phone, open an iPhone, and you look at how much space. So if you have an iPhone like this, and you look at how much space is taken up by the power circuits, anybody have a guess?
60%.
Yeah, you have about 60%, 50–60% of your phone is a power circuit. Okay, so a lot, if you want to work in Apple, one thing, there's different jobs. So actually what Apple is, a lot of times are looking at for people who can design this for power circuitry. Okay, we're no longer limited by the scaling in the chips, in the microprocessing chips. We're increasingly limited by the power circuits. And how to make the power electronic circuits smaller, right? So Moore's law basically did nothing, had nothing to do with the power circuits. There's no Moore's law for us, right? So, but how do you, scale? Can you make all those things smaller, right? So if you really want to make a phone, that's very, very, the very thing, right? If you want to make a phone that has a very small form factor, you're pretty much limited by your power circuit, by the size of your inductors, capacitors, and your power electronic switches, because that's the limitation. Right? How do you do that better? As a very hot topic, right? There's sort of many people doing that. So we are going to do simple calculations, but again, keep in mind that if you look at innovation, especially in hardware, both in the renewable space and in the, let's say, the devices, right? The sort of the technology space, the mobile phone space, the laptop space, both of will be driven quite a bit by the power electronic design. How do I make these things? How do I make them smaller, more efficient? So having said that, for us, again, our switches as a bipolar transistor. So this is our switch. Okay, so our switch is a bipolar transistor. What this does is you can control the amount of current you pass through this through the base, right? By controlling the amount of current through the base. We won't worry too much about the equations. We'll just, we're going to say this is approximately this switch, or approximately this type of switch. All right. So anybody know what's the other type of transistor we have? So bipolar is one. What's the other type?
MOSFET.
MOSFET. So why do we use bipolar? Right. So what's the
question?
All right, go ahead.
Sorry, what was the question?
Right. So here I said the switch is a bipolar transistor, right? Why not a MOSFET? For every other application, you use MOSFET. Right? So you look at your interior computer, everything on your chip is MOSFET. It's not a bipolar. But why for power electronics do we use bipolar instead of MOSFET? Remember the difference between these two? Right. So it turns out, what it turned out to be is bipolar is more robust. You can actually push a lot of current through bipolar. Okay, there's sort of this sort of current control drive. Right? It says current, it's a current-driven device. And it turns out, you can just pass a lot of current. It's easy to make. It's robust. Okay. Whereas MOSFET is lower loss. MOSFET is tremendously it's a lot more efficient because it's a voltage driven. So at the gate, you apply a voltage, and you have an insulator between your gate and the rest, right? And the rest of the transistor. But that has problem tolerating high current in the past. So in the past, we have been using bipolar more often than not. But today, there's a technology shift towards using more MOSFET. MOSFET can be made smaller, can be made lower loss, made more efficient, and so on. So if you actually go into industry now, you may see MOSFET. Okay? So don't be surprised if you see a circuit that's a power transistor being a MOSFET. Nowadays getting more popular. But bipolar is, for example, the things you use. If you take 351, the thing you use in the lab is a bipolar transistor. It's easier to make. So it's a bulkier, cheaper version. Right? So that's one, our bipolar. Then we have, our old friend SCR, right? So SCR is a device that can turn on and off based on the amount of current you pass through it, right? Or the voltage you pass through it. Okay, so we have a triggering angle, and then we can, because based on what that triggering angle is, we can shift how much current you pass. Okay, so this sort of controllable diode. Right, so our SCR is basically a controllable diode. It's a diode where you can control the turn on voltage, right? Or turn on voltage of the diode. Okay. So CR, you open at a triggering angle, you can close at another angle, or you just close when the current is going through you as 0. So we like SCR quite a bit in power applications, right? For the precise reason you have seen in type 1 and type 2 turbines. Okay, can dynamically, right? This triggering angle gives you a control variable. And this control variable can dynamically control something like the outer resistance. Okay, so that's the why we use SCR. Right? A lot of times use SCR. So yeah, so basically it's a combination of a diode and a bipolar transistor. Okay, so SCR is basically you take a diode, you squash a bipolar transistor into it, and you get SCR. That's sort of how you make this type of things. Any questions with the bipolar transistor, the SCR? Okay, so I'm going to assume, again, we have all seen this, and this is just a basically reintroducing make sure we have the same terminology for this kind of thing. So when we do converters, right? So of course there are 4 types of converters. Right? There's a AC-DC, DC-DC, DC-AC, and AC-AC converter. So this is colored a little bit differently because AC-AC is, a trans, right? So this is not a transformer. Okay, so right, a transformer is an AC-AC converter. It converts AC waves to AC waves by changing the voltage, right? So when we say AC-AC, we don't mean a transformer or a traditional transformer. What we mean is AC-AC is really 2 converters back to back. Okay, what we really mean is a sort of chain converter back to back. That's our AC-AC converter. So next we're going to go through different types of converters, right? So we're going to only go through AC-DC, DC-DC, and DC-AC, because the AC-AC converter is really a sort of combination of all the other 3 types chained together, right? So let's take a look at the AC-DC converters. So the first thing is, let's say I have an AC wave. I want to get a DC wave out of it. How do I do this converter? Okay, so and here for us, DC means, so what does DC mean for us? DC means something with non-zero mean. Okay, so for us, this is a DC. Okay, so for us, this is a DC waveform. Right, so what we're not going to do is we're not going to worry too much about filtering this waveform. Okay, so for us, AC is something that sinusoidal have 0 mean. DC is something that has non-zero mean. It doesn't mean it's a flat. It doesn't mean the voltage, for example, is a constant. Okay, that's achieved through filtering, right? But the filter design is beyond the scope of this course. That's something you do. I know many of you have taken the power electronics classes. You do more of, you do that there. For us, what DC is a curve that's positive. Okay, so this is a DC curve for us. Okay, so don't think DC means a constant voltage. DC just means something that's doesn't average out to be 0. This is our DC conversion. Okay. Right. So the easiest converter we have is, of course, this half wave converter. Right. We have a sine wave. We have a sine wave. We pass through a SCR, and I allow about half the waves to pass through. I allow half the waves to go through. Okay. So to drawing this out, as if I have SCR, what the convergence what the circuit is the input waveform. So this Vs, I'm going to draw Vs with this blue. So my Vs is, I said this curve, this is Vs. Okay. Look at Vt, which is the voltage I get as the output of SCR, right? And as we all remember, this is my Vt. So I have this kind of curve, right, where I turn on at alpha. This is my triggering angle, and the current you pass through as Vt over R. Right? So you act like a wire once you turn on, and then you turn off once you get to the, let's say once the voltage crosses 0 again. Okay, so this is our voltage profile, right? This is SCR. Okay. So this is right. So this is our SCR. So what we care about is the average voltage. Okay. So there's two voltage we care about. Right, there's an average voltage. What's the other voltage we care about in the circuit? Right, so we care about the average voltage, right? We care what the average of this, what this average ought to be. What is the other thing we care about? The other quantity in addition to average? We remember what's the other voltage? Right. So the other thing we care about in addition to average is RMS, right? That's not the peak, not the peak. Okay, so there are several answers. So some are RMS, that's correct. Peak voltage we typically don't worry all that much about in the circuit, right? Because the peak is the same, right? The peak for the VT and VS, they have the same peak, right? But they have different averages and different RMS voltage. Okay? So one is average, one is the RMS, the root mean square voltage. Okay? We want to compute these two voltages for our circuit. Okay? So let's compute the average voltage. Right, the average voltage, if you have something that turns on at the triggering angle alpha, turns off at the commutation angle beta, then the average is basically you integrate 1 over 2 pi and integrate over 1 period. That's sort of the average we have. Then for simplicity, we're going to assume beta is 0, beta is pi. So you turn off when the voltage crosses 0. Okay, so we're going to turn off when the voltage crosses 0, beta is pi. Then in this case, if you compute the average, then the average is 1 over 2 pi, integrating alpha 2 pi sine t d omega t. This is fairly simple. This is V max. Alpha 2 pi, V max sine omega t d omega t. So we get the average voltage is V max over 2 pi 1 plus cosine alpha. And then, of course, the average current is the average voltage divided by the resistor we have. Okay, any questions about this? So the max, yeah. So this is average. What about power? What about power? Right, so is power, let's say, is that how we compute power? Right, do I just multiply the averages together? Okay, so this is obviously not the case, right? So power is not, right? So this is power is not the averages multiplied together. Okay, power, that's not how we compute power. But this is again a common mistake people make. As you compute average voltage, the average current, and then you say, okay, you know, voltage multiplied by current is power, right? Since these are average quantities, and I get the average power. That's not quite true. Okay, that's not quite true. Right? So why isn't this true? The reason why it's not true is power, right? The instantaneous power is something, you know, as a VT, squared over R. Okay. So since this is not linear, you cannot take average then multiply. Okay, so the tricky thing is if you want to compute power, you can, because of this square, this nonlinear operation, you cannot say I do average of the two quantities that multiply together and I get power. Okay, that's just not the way for this, the math works out. Okay. So to compute power, we need to compute the RMS voltage, right? So instead of the average voltage, we care about the RMS voltage. So the RMS voltage, this is again a very good name for the voltage. This is a root. You take a root, you take the mean, and you take the voltage squared. Okay, so it's a very good name. It literally describes how you write down the equation, right? So you do the root, then the mean, then the square of the voltage. We can compute this. You can basically compute the integral. We're not going to care too much about how exactly you compute it. It's not a very difficult one to compute, but nevertheless, we can integrate and get this answer. Okay. So this is the answer you get by integrating the whole thing out. So this is the RMS. So if you the last thing we want to do is we want to compare VRMS to the VSRMS. Okay. So remember, right? So our input. How do I want to say this? Yeah, this is okay. Yeah, so this is RMS. So let's I think let's keep it this way. So this is RMS. Okay, this is the RMS voltage we have in our circuit, right? And our power, if this is RMS, then the power is given by P as VRMS squared over R. Okay, so it's not the average voltage squared, but the RMS voltage squared. This is the same as IRMS squared times R. MS over R. So power is V max squared 8 pi R. Pi minus alpha plus sine 2 alpha. Right, so this is our power equation for things going through the SCR. Right, so by changing the triggering angle, we can change sort of how much power that goes through this SCR. Any questions about SCR? Okay, so SCR will act like a basic building block for us. So SCR is our basic building block. That's how we'll construct sort of the other circuits we have. It's how we will construct the other circuit we have in our system, right? So again, you can think of SCR as this control switch. You can think of SCR as a switch that can be controlled. So it's not just, a zero, right? So it's not it's sort of a way to control how much power you let through, right? So this way to sort of a graceful way of controlling how much power you let through the switch, right? Or how often the switch is on and off. Okay, so this SCR. So everything else will be built out from this equation, this basic equation. So I need to end the lecture a little bit early today. I have to run just a little bit past 2. So let's end the lecture here. Next class will very quickly, so we can go through the rest of the converters fairly quickly once we have these basic equations for the power path through SCR. Okay, we'll run through the power electronics, other converters fairly quickly. Then we get into type 3. Okay, we'll look at how do we design a type 3 turbine, where we don't want to use, we don't want to do all the control through a added resistance. Rather, we want to do control using, let's say, a AC to AC converter. Okay, and the midterm covers to type 2, to the end of type 2. So to this week's homework, to the new homework that's out today. Okay, right. So if no questions, let's end the class here today, and then I'll see you next Tuesday. And as a reminder, so now the office hours are on Monday afternoon. So the office hour on Monday afternoon, I have a lecture on Tuesday, and then the midterm is next Thursday.
Thank you, Professor.